Hey guys, this is a little quick video on buffers and what they are, how they work, and then calculations based on their pH. Now the idea is that if I were to add acid to water or any neutral solution, even if I add a small amount of the acid, let's say I have 100 cm cube of water and I add acid to that. Now what happens is that the pH drops. So this graph is exhibiting the changes in pH when I add about 10 cm cube of HCl to 100 cm cube of water. So I've taken 100 cm cube of water or neutral solution and I've added 10 cm cube of HCl to that. Before adding HCl, the pH was 7 and there is a sudden drop and it levels off to about 2. So the pH changes from 7 to about 2. That's a large change in pH just by adding 10 cm cube of HCl. What HCl? About 0.1 mole per dm cube HCl. Not even 1 mole, but 0.1 mole per dm cube HCl. And the reason I'm saying is this, that because what we want is we want to find a solution that doesn't do that. Theoretically, a buffer is a solution where if I do the same thing to a buffer, the pH would not change. Yes, it won't start at 7, but at least it wouldn't change. The change is what I'm concerned with. So normally, if I add acid to water or any neutral solution, the pH will go from 7 drastically down to 2. But a buffer whose starting pH might be 5, might be 4, might even be 8, 9, later on we'll see. But if I add a small amount of acid to that buffer, theoretically the pH should not change. Now, I'll give you an idea. For example, I'll tell you what a buffer normally is. A buffer is normally made between an acid and a salt of the acid, or a base and a salt of the base. We'll talk about why later. But let's say I tell you that I have a mixture of ethanoic acid that you guys know of, that we've studied. That's a weak acid. We know it's got a Ka. We know it's about 1.7 to 1.8 times 10 power minus 5. And to this acid, I've also added a salt, which has its anions. Let's say a sodium salt to this. Now, the trick is that I have an acid and a salt of the acid. Now, if I make a mixture, this is what we call a buffer. Now, how this acts as a buffer, we'll explain that later. But the overall effect, why is this called a buffer, is because the graph that you guys saw, this one, and I'll zoom on just a bit, is that this is what would happen to the pH of this solution if to this solution I added HCl. What I mean to say is that if I took, unlike the previous case, if I took 50 cm cube of this and 50 cm cube of the salt and I mix it together, what will happen is to that, if I add, let's say, H plus ions, let's say HCl, the pH would go from, let's say, about 4.76 to 4.74. Yes, there is a slight change, but it's a very nominal change. Meaning, to this buffer, if I added an acid, the pH would hardly change. Similarly, if I added NaOH to this mixture, the pH would go up, but very slightly. It'd go from 4.76 to 4.78. Again, not much of a change. If you had seen earlier, and I'll scroll back up, when I did the same thing with water, when adding acid to water, the pH went from 7 to 2. And if I added NaOH to this, it'd go from like say 7 to 11 maybe. But if I had taken a mixture of ethanoic acid and equal amounts to that, add a salt of ethanoic acid, and that mixture, which we will call a buffer, its pH hardly changes on adding small amounts of HCl or any other acid or small amounts of NaOH. The idea being that the pH remained virtually unchanged when we added an acid or added an alkali. And that's what buffers are. So by definition, what are buffers? Buffers are solutions that can resist changes to pH when small amounts of acid or alkali are added to. Let me repeat what I said, and I'll write it down. Buffers are solutions that can resist changes in its pH when small amounts of acid or alkali are added to them. And the example was given in this case. When I added 10 cm cube of acid to this buffer, 10 cm cube of HCl, the pH hardly changed. hardly decreased. And if I add NaOH to this, the pH also hardly increased. Now, what makes something a buffer? Generally, what we've seen is that it just only has two components to it. Like what you saw, Abhi, in my example, you had, ethanoic acid, which was CH3CO2H, CH3CO2H, and you had a salt of the acid. Now, generally, a buffer will always have two components. And the reason why you want to have two components is because one of them will act with H plus ions and neutralize them, any additional H plus ions that you add. Like in this case, what you'll realize is that this CH3CO2Na is a conjugate base of CH3CO2H. What that means is because it's a base, it can react with H plus ions. And on the left hand side, ethanoic acid is an acid. So how does it act as a buffer? Because it can react with alkalis or OH ions. It can react with, let me just write it down, react with OH minus ions. And that's what you want. The reason why buffers resist changes is because when you add an acid, the buffer has something to neutralize the acid, or to basically not neutralize. The correct term is to use up the H plus ions that you add from the acid. And they also have, and in this case, that would be the base. In this case, this right here. And if you have an alkali, if you add an alkali, which is hydroxide ions, it must have something to absorb or to convert the alkali or OH ions to something else, because you don't want OH ions coming in. Because understand this, that AH ions will decrease pH, and OH ions will increase pH. And the reason why OH ions increases pH is because when water ionizes, it has equal amounts of H plus and OH ions. But if you add extra OH ions from outside to maintain the same amount of H plus, the same Kw, the H plus decreases, because remember, Kw is H plus into OH ions. And if you increase one, you decrease the other. Now, what you realize is that in this example, a buffer will always contain an acid part and a base part, and both in some considerable concentrations. Because the way they're designed is that they have to keep the concentration of hydrogen ions and hydroxide ions in the solution unchanged. That's why pHs won't change. Whatever the buffer is, it will not want to change the concentration of H plus ions or OH minus ions that already exist, which means that if you add acid or alkali, it has to use up all of what you've added. Okay? And they're based on an equilibrium, which changes direction to absorb the additional acid or alkali. That's what it is. Generally, acid buffers are two kinds: acid buffers and basic buffers. And we'll talk about acidic buffers first. So we are talking about acidic buffers here. Okay, they are made from weak acids. So now, for example, ethanoic acid is a good weak acid. Now, the reason why it's a weak acid is because it only partially ionizes in water. Now, I made a simplified version of this, but ethanoic acid, like in this case, the guy right here on the left, is a weak acid, and it is the acid in the relationship. And when it dissociates, when it loses a proton, the remainder is what we call a base. So the conjugate base of acid is this. And you might think, well, I have the acid and I have a base. Why can't this act as a buffer? There's only one problem. In this scenario, the acid is in pretty high concentration. This square brackets, let me remind you, always imply concentration. So me writing like this, the acid concentration is high. And the reason why the acid concentration is high, because if I take ethanoic acid, it hardly ionizes. So most of it is in the unionized form right here. Now, the problem is, because most of it is unionized, there is a very small amount of H plus ions and very small amount of the base also. So basically, your conjugate base key concentration is low in this case. You might say, well, H plus is also low, and that is low. And that's why the pH for this case is about, 3. But who cares about the pH, initial pH? We don't care about that yet. We care about not changing it. The problem is that the base is low. And why is that a problem? The problem is that in this scenario, if I were to add NaOH, the NaOH, let's say, would act with which part of the equilibrium? The NaOH will be neutralized by the acid. And we have so much of the acid that it reacts away. Now, and I'll write the answers, the detailed version of this also. But let's take this for example. Now, let me go back again. So the idea is that, let me take NaOH. So when I add NaOH into water, this is me adding NaOH solution to my acid. Now, what is NaOH solution? It has Na plus ions and OH minus ions. It's the OH minus ions that are the problem right now, because OH minus, if I were to add OH minus ions, they'll suddenly increase the pH, because they will increase pH, because POH will decrease and pH will increase. So our job is, if I'm adding NaOH to my buffer, the additional OH ions should all be absorbed. That is the purpose of why creating a buffer, because a buffer's point is to be able to absorb any small amounts of acid or alkali added. So what I'm saying is, if I were to add NaOH to my buffer, the idea is that the extra the OH ions added from right here should all be converted to something else, because if they're not converted, they will increase pH. Now, in this case, what happens to these OH ions? These OH ions are then going to react with CH3CO2 minus H, CH3CH2H. Now, where did this come from? Because remember, I told you that we are working with an acid buffer, and for now, I only have ethanoic acid. So I have ethanoic acid, unionized, most of it is high, and these two amounts are low. And when I add NaOH to this, system, understand that I'm adding a small amount of NaOH. So the OH ions that I'm adding, I'm going to react with the acid part. But because the acid is pretty high in concentration, when they do react, it hardly changes the concentration of the acid. But even if it does, it creates my base and water. So the OH ions that are added react with my acid to make base and water. And what you need to understand is that, yes, acid is decreasing and base is increasing in this reaction. Whatever OH ions I added as an external thing, the acid decreased by absorbing it and converting it into a base and water. But what's definitely missing from this equation is any H plus ion, which means there is no H plus ion decreasing or increasing. All of the OH that you added is now being used up. So there is at this moment, all OH ions added, or approximately all, are used up. Now, this can only happen when the OH ions is much less in quantity than the acid. But generally speaking, that's what buffers are made. They're only made for small amounts of H plus and OH minus additions. If you add too much of this, you'll end up using all of the acid. And when you use all of the acid, there's no acid left to make H plus ions. Anyway, so we are here talking about a small amount of OH ions being absorbed by the acid to make the base. All the OH ions that are added from NaOH are used up, which really means, yes, so the acid is going to decrease somewhat and the base is going to increase. But understand that this will have no effect on H plus ion concentration. That stays the same. It stays almost the same. And the reason for that is because that came from the ionization of the acid, which decreased, but it decreased only by a bit, so it doesn't affect that. The problem happens is that if to the same acid, so this is acting as a buffer. So at this stage, ethanoic acid is acting as a buffer because this guy was in high quantity. Let me scroll back up to show you what I mean. So when acid was ionizing, there's a lot of unionized acid, which we've used up some of right now to react with the OH ions. But now to this system, if I were to add H plus ions as a secondary thing, that would be a problem because the H plus ions will have to react with the base, and the base is low in concentration. So let's say I added HCl. Now when I add HCl to this, HCl will give me H plus ions and Cl minus ions. The problem is the H plus ions that I just added, these are the additional H plus ions added, have to react with the base. The base in this case was CH3CO2 minus to make the acid. That's how the base reacts. It becomes a proton acceptor. The only problem in this scenario is that I don't have enough of this because this was very low in concentration. The reason is that the acid didn't ionize much. Remember, the acid didn't ionize. I know I'm repeating this, but I need you to understand that if I just take a pure acid, it has a pure weak acid, it has lots of unionized acid, but very small amounts of the base that is ionized and H plus ions. And if to this system I did add HCl, the problem would be that the HCl that I just added would not have enough base to react with. So what I'm saying is here that not all of the H plus ions added will react with the base. And the reason for that is there's not enough base. So some H plus ions are left over from HCl. And if they are left over, what will happen? They will increase the net concentration of H plus ions. And what does that mean? It means the pH will decrease. And if that happens, then this is not a buffer. What we want is, we want something to absorb all the H plus ions added. Well, the one way to solve that would be, well, if I have lots of H plus ions, I should have lots of base ions. So where do I get the base ions from? That's why we took ethanoic acid and a salt of ethanoic acid as the buffer. Because if I did the salt now, understand that the salt will provide a lot of these ions. So when the salt is taken, it will then also fulfill this second half. Because the acid, the ethanoic acid, was helping us remove all the OH ions. That part is acting as a buffer. But the H plus part, it needed a base to react with. There's not enough base ions. So what we do is, we add the base ions separately from a salt of ethanoic acid. Which means that to help this out, if I had ethanoic acid and a salt of ethanoic acid, so the salt of ethanoic acid would ionize completely to produce this. And when I have salt of, and this is the conjugate base, remember the salt is the conjugate base of ethanoic acid, which is my acid. Because it's a salt, it will fully ionize. So see, it fully is ionizing. What that means is that this guy is going to be in high concentration. So now my ethanoic ion concentration is not just coming from the acid, it's coming from the acid, which I saw already, the acid ionizing, and it's also coming from the salt. The acid amount is very low, the salt amount is very high. So the point here is that the salt amount is very high, and so when we're considering the conjugate base concentration, we'll take it from the salt. This is about 100 times more than this. And now I have the solution to my problem. Meaning that now in this mixture, if I add H plus ions, they will be absorbed by the conjugate base, because now I have lots of this. So now it doesn't matter if I add H plus ions, because they will right away be converted to the acid. And therefore it would not increase H plus ion concentration. Now, that's how buffers work. The idea is simply this, that you're supposed to have a mixture of a weak acid and a salt of the weak acid. Why? Because the weak acid will give you a concentration of the acid, unionized acid, as high, large amount of that. And the salt will result in a high concentration of the anion, which would have been less if I had only taken the acid, because the acid only partially ionized. But because I'm now taking a mixture of almost equal amounts of salt also, the concentration of the anion is also high. Yes, H plus ions in this state is low, but we'll talk about that. We'll calculate them later. We don't care about what the initial value H plus ions are. We care that it doesn't change. So now if to this mixture I add H plus ions, like from an acid, I additionally add H plus ions to this mixture, then the base will react with it and absorb all of them. And if to this mixture I add OH minus ions, then the acid will absorb. So literally the exam will want to know how this solution will act as a buffer. So you say, if I'm going to, let's say additionally I add H plus ion what will happen is the H plus ions will react with the base. The base is the conjugate salt or conjugate base or the salt of the acid. And what this equation shows is that whatever H plus ions that you add are converted by the base into the conjugate acid. But they don't stay in solution, so the pH doesn't change. Similarly, if you add OH minus ions, then they will react with the acid to convert itself into the base, and obviously it makes water also. So some of water is also made here. So now this mixture contains the mixture that we have, this weak acid and the salt of the weak acid, has been able to absorb both H plus ions and OH minus ions. H plus ions that you add react with the base to convert into the acid, and the OH ions that you add react with the acid to convert that into the base. And so no more OH ions that you've added are in solution, and no more H plus ions that you added separately are in solution. All right. Yes, it will decrease. For example, if I add H plus, it will decrease a bit of this and increase that, but will not change H plus. And if OH ions I add, it will decrease a bit of this, increase a bit of this, but not change H plus ions much. So what you just saw was basically an acidic buffer. An acidic buffer has two parts to it. Generically, any acid buffer, it has HA and let's say a sodium or potassium salt of the acid. And the reason why that helps is the HA is the way I represent my weak acid, okay, and that helps me to absorb OH ions, and the salt would be my conjugate base. So whatever formation you have, whatever compounds you have, the mixture will always have the anion the same in the acid and the salt, because the anion is the conjugate base. So when you add externally, when you add H plus ions or any acid to this buffer, they will react with the base, which is the A minus, to become the acid. So all of the H plus is absorbed. And if you add OH minus to this system, then it will react with the acid, which is HA in this format, and convert it into the base and water. And it doesn't, as long as you have a large amount of acid and a large amount of base, it will be a buffer. This type is called an acid buffer. You also have basic buffers, and in that case you'll still need an acid and a base, but the roles are switched. For example, let's take ammonia. So a basic buffer would also have a weak, instead of weak acid, you'll have a weak base like ammonia, and you'll have a salt of the weak base, in this case NH4Cl. Why? Because ammonia is your base now, and NH4Cl may you have NH4 plus ions, which are your conjugate acid. And why does that help? Because now if to this system I add H plus ions externally, they will react with the base to become the acid. In this, you'll realize that's the generic reaction of how buffers behave as buffers. Any acid you add to the buffer will react with the base part of the buffer to convert them into an acid. And any alkali you add to the buffer will react with the acid part of the buffer to make the base. Let me repeat. In this particular case, the H plus will react with the base. What is the base? In this case, ammonia. And make the acid, which is NH4 plus. See, NH3 plus H plus becomes NH4 plus. And OH minus will react with the acid to make the base and water. And this is how buffers react. Okay, that's literally what they are. Okay, let me show you the diagram here. Now, generally speaking, a good buffer would have, this is the focus here now, a good buffer would have an acid part and a conjugate base part in equal amounts, and there will be some H plus ions, but the idea is that they have both of them in good amounts, so that when I add H plus, some of the A minus will absorb that H plus and make more of the acid, and some of A minus is used up. But all of the H plus is now absorbed, so there will be no change of pH. And if I add OH ions to this buffer, then they will react with the acid to make more of the conjugate base. But all of the OH minus ions will be used up. and therefore would act as a buffer. And that's really what the buffer's use is. And you will be asked to literally क्या कहते हैं, be able to come up with equations for it. So always remember this. And it's a 2-mark question always. How does something act as a buffer? Well, the acid part of the buffer will react with OH ions to make the conjugate base and water. And the base part of the buffer will absorb any H plus ions that you add to make the acid again. Okay, so I'll show you a couple of examples. For example, they'll say, you know, a very popular question a few times has come is that how does a mixture of sodium hydrogen phosphates act as buffers? Now, this is the mixture of 2 salts of sodium, and you might wonder, whoa, what is this? Well, it is a buffer, and the reason why it's a buffer is because it's got 2 anions, H2PO4 minus and HPO4 2 minus, and one of them is considered the acid and one of them is considered the base. And to show you that is always the acid has more H plus. So I could show you also how this is an acid, because it would ionize to produce HPO4 2 minus and H plus. So between the 2 anions, the H2PO4 minus is the acid and HPO4 2 minus is the base. Now how would this act as a buffer? So now they'll ask you to show how this acts as a buffer, and the way to show that is to realize that if you add H plus ions from an acid, they will react with the base. In this case, the base is HPO4 2 minus, and it will become the acid again. So the idea is this equation is showing you whatever H plus that you added to the buffer are absorbed and converted, and they didn't change the pH. And if I add OH minus ions, they will react with the acid part and convert that into the base and water. All right? And that's really what you have to show for the exam. That's it. And defining a buffer. So what's a buffer? A buffer is a mixture or a solution that resists changes to pH or has almost effectively no pH change when small amounts of acid or alkali are added to it. And the exam can ask you, well, then how do you write the equations of something acts as a buffer? Or show how something acts as a buffer. So they'll give you a mixture of the buffer. Here I give you a mixture of sodium hydrogen phosphates, the 2 hydrogen phosphates, dihydrogen and hydrogen phosphates, to show you how it acts as a buffer. So I've identified the acid and the base. So the H plus reacts with the base with the less H's to become the acid. And the OH ions will react with the acid to become the base and water. Alright. This ends the first video on buffers. There will be 2. This one was about what they are and how they act. Okay. And the next one is about, it'll ask you also to calculate the pH of buffers. So meaning that now that we have made a mixture of things like ethanoic acid and sodium ethanoate, how would I calculate the pH of that? Alright. And that's coming by the next video. This one is done. Over and out, guys.